Well, welcome everybody to this latest webinar, Reducing Ice and Mist in Freezers and Cold Stores with Dehumidifiers. My name is Dave Marshall-George and I'm the UK and Ireland Sales Director for Condair, and I'm joined today by Julian Tasho, who is one of our dehumidifier experts, and Julian's going to be answering some of your questions in the background. You will notice that you've got a control panel for the webinar, and in the control panel there is a box where you can ask questions. So please feel free as we go through the webinar to type in a question, and Julian in the background will either answer your question or we'll have time for some questions at the end of the presentation. The presentation should last 40 to 45 minutes, and again we'll have some time at the end of the presentation to ask some questions, and we may discuss some of those technical issues. You'll also notice that there are a couple of handouts there. There's the Condair Guide to Dehumidifiers, and there's a copy of the presentation. And you'll get an email after the presentation to say that you have successfully achieved an hour of continual professional development. So without further ado, we'll continue with the presentation. We're going to turn our cameras off so you can concentrate on the slides, and we will dive into the presentation. So just a little bit about Condair. Condair are a global organisation. We're one of the biggest humidifier manufacturers and humidity control equipment manufacturers in the world. We manufacture out of Ottawa in Canada, out of Hamburg in Germany, in Rouen in Denmark, and in Beijing in China, and we have global distribution. So let's take a look at what we're going to look at today. We're going to look at how to what humidity's impact is on freezers and cold stores, and that could be icing up in cold stores, it could be ice forming in evaporators, it could be ice forming on products, it could be ice forming in on safety devices, it could be having a produce aroma or flavor altered by ice crystals. It could be many different things that we look at. And then we're going to look at how to manage humidity. What devices, what mechanical units are we going to use to manage that humidity and reduce the humidity so we don't experience ice formation or we prevent ice buildup. We're then going to look at installation options. Do we put a dehumidifier inside the room? Do we put it outside the room? Where are we going to draw the air from and send it to? And there are different considerations for different options there. We're also going to look at some energy considerations. Where are we getting the energy from to run the dehumidifier? What effect that's going to have? And then we'll also look at sizing and selection, what we need to know in order to be able to select and size the appropriate type of dehumidifier for the application. So we're going to start by looking at what are the causes of ice forming in a freezer. So we've got a nice graphic here of our freezer room, and the first point of, that we're going to look at is moisture from produce. When we're bringing produce into the freezer store, we can get moisture coming in from the product, and that can be whether it's from its production process or its storage process. If we've got a change in temperature, we may get ice forming on that packaging, and then that can have a detrimental effect on the integrity of that packaging. So we can get moisture coming from the product that's going onto cardboard packaging, or indeed to go and form ice in the cold store. We've also got people operating in the cold store, and people are emitting moisture. We're breathing and we're sweating. And the amount of moisture that's going to be emitted from a person will depend very much on the rate of work that they're doing. And we tend to use 3 different rates of work for sizing of dehumidifiers. We'll have a certain amount of moisture that will come from somebody at a moderate rate of work, then a higher rate at a medium output of work, and then a higher rate if somebody's really working hard and breathing heavily and sweating a lot. So that moisture is going to come from the people into the cold store and again can form ice. Moisture from entrances is really the biggest form of moisture that's going to come into the space. And this is really where we've got an entrance. We've got two different temperatures, both inside and outside the cold store. Well, we've got two different temperatures and two different humidities. We get an imbalance in vapor pressure. And vapor pressure will always try and equal out. It will always try and go from the high to the low. So when we have that difference in vapor pressure between the outside and inside, moisture will be forced into the cold store from that doorway. So it's critical to know how many doorways we've got, what is the temperature difference between those doorways, and also what are we doing to mitigate that air change rate. Have we got strip curtains? Have we got polar strip curtains? Have we got air curtains? Have we got fast-acting doors? Have we got some way of mitigating that open door? Have we got a robust regime that we're educating our staff to have to keep the doors closed? So moisture is going to be coming in through that doorway or even an open conveyor hatch at a rate relative to the difference in vapor pressure between the outside and inside. And the effects, they can be quite significant. Again, we mentioned on stored goods, this can have an adverse effect on produce. If we have ice crystals forming on produce, it can have an adverse effect on aroma and flavour. And of course, we mentioned on packaging, it can have a terrible effect. Systems. Well, systems, we've got an evaporator or a cooler. So we've got an evaporator here. Inside that evaporator, there's a refrigerant that's boiling, probably 6 to 7 degrees C below the store condition. So you've got, let's say, a store condition of 27 degrees C, minus 27 degrees C in this store. Well, we've probably got an evaporating temperature of minus 33, minus 34. And an effective appliance surface temperature of maybe minus 31. So any moisture that's going to come into contact with that coil potentially can freeze. And it's usually the first place that it does freeze because we've got fans moving the air and circulating air. So more of the air is going to come in contact with that evaporator coil. So then we get ice forming more readily. But that's not the only system. We could have smoke detection systems. Smoke detection systems have very fine filters in them, and small ice crystals can block up those filters very quickly. We could have fast-acting doors. We could have switches on those doors that are going to be affected by that ice. So systems can be dramatically affected by ice in the space. And we've also got surfaces where ice can occur. Now, on the walls and floors, and very commonly in the ceiling above the doorway, as that moist, warm air comes into the cold store, it rises up because it's warmer than the other air around it in the cold store. And the first thing it hits is the ceiling. And initially that will condense into water, but very quickly it will freeze. And at some stage, somebody has to remove that. And there's quite a lot of effort and energy and potentially downtime in your freezer where that ice has to be removed. Fogging is also very common, and typically fogging is going to occur when the relative humidity is very high and we're typically 2 degrees C below dew point. Fogging will occur when moisture has saturated the air and it's suspended in the air. And this gives you a problem if you're moving heavy machinery around. It is a health and safety issue. You've got stored goods on pallets, you've got forklift trucks, you've got people moving around, and even though they're in high vis, fogging can cause a dramatic loss of visibility within that store. So getting rid of that fogging is very, very desirable. And we have, of course, slips and trips. We've got ice on that floor, and we've got operatives working. So we've got a potential health and safety hazard especially when you put together lack of visibility and ice on the floor and surrounding areas. The potential for an accident is very high. So where does the condense in the air come from? So I'd like to draw your attention to the column at the right side of the slide here. And let's imagine this is a column of our air. And our air here is at 35 degrees C, and the percentage saturation is 40% RH. But our absolute humidity, so this is actually the amount of water that's in the air, is shown at the bottom. It's 0.01480 kilograms per kilogram. And when we look over to the left-hand side, we've got a psychrometric chart. And just to take you through the basic elements here, at the bottom we've got our temperature going in degrees C, up from 0 up to, in this case, 50 degrees C. And you can see the relative humidity in these curves. That's 10%, 20%, 30, 40, right up to saturation point. And our air is sitting just around here, 35 degrees C, 10, 20, 30, 40% RH. And we've got a moisture content of 14.8 grams. And that's fine. But what happens when we cool the air is that air contracts, but the amount of moisture in the air stays the same. So if we contract this air, you can see now that the temperature has dropped. So we've cooled the air down to 24 degrees C, but the amount of moisture in the air has stayed the same. So our relative humidity, so the percentage saturation, has increased, but again, my absolute humidity has remained the same. And this is reflected in the psychrometric chart. When we sensibly cool the air, we see the effect is that we see a decrease in dry bulb temperature, but we see an increase in relative humidity. That's 14, 15, 60, 70%, and so on. But the absolute moisture content is remaining the same. It's the capacity of the air to hold the water that is changing. So that's okay. We're cooling the air sensibly, but eventually we're going to reach a point where the air is 100% saturated. And at this point, well, we've come down to 21 degrees C on our site chart. And I'm now 100% saturated. But I don't want my cold store or my freezer store to be 20 degrees C. I want it to be much colder than that. So what happens then is that to go through our first phase of cooling, we've reached saturation, and we then further cool. And as we follow that curve down, the temperature drops, but of course the air can't hold as much moisture. So moisture falls out of the air. And again, because the air is being circulated by the evaporator fan, the evaporator is typically the first place that moisture will settle on. So we've contracted that air and cooled it right down to, let's say, minus 27 degrees C. Relative humidity is still at 100%, but now my absolute humidity or absolute moisture content is 0.00032 kilograms per kilogram. So I've released all of that moisture into the freezer store, and that is going to, because it's below zero, is going to form ice inside your freezer. So where does this ice come from? So ice and mist will form at any point where outside wet air can enter the store and meets the inside low temperature. And this is what it would look like. And you guys will probably be familiar. Here you can see ice forming around a freezer door. And that's interfering with mechanical elements of the door. It could be interfering with lighting. It could be interfering with exit signs or safety signs. And certainly affecting the efficiency of that strip curtain. It could be around a vent. If we've got air being poured into a cold store from a vent, then we can get ice forming around that vent as that moist warm air comes into the cold room and it immediately hits that colder temperature and the moisture starts to freeze. Ceilings and floors. Again, here you can see a ceiling, and it's very common. It's on just above the entrance to a cold store where air enters the cold store. It immediately rises up, it forms condensation, and that condensation goes on to freeze very quickly, and we get significant ice buildup inside the freezer store. And mist formation as well. This is a pretty good example of mist formation where relative humidity is just below dew point. And again, we can see that we have got a health and safety issue here with visibility for operatives. And certainly if you're moving any heavy equipment around there, such as a forklift or a pallet, then we've got a significant, and again, health and safety issue. And then, of course, we've got equipment surfaces. So it takes a little bit of an explanation for this photograph. And for those of you that are familiar with cold stores will know this is the rear of an evaporator. So we've got the fans on the opposite side of the evaporator. This is a ceiling mounted evaporator where they're coming over this coil. And you can see that the coil is a solid block of ice as we've got air ingress into the cold store, and air is being circulated over the evaporator at a high rate, and of course we've got that accumulation of ice in the evaporator. And this picture tells pretty much the story of all of those conditions. We've got cardboard patching that's got ice forming on it, and that's starting to be deteriorated, lose its integrity. We've got fog forming at the top of the cold store, so we've got a visibility issue potentially. And we've got ice on the floor, so we've got slip hazards for operatives. And we've got the evaporators starting to ice up as well. So we're going to lose efficiency, and we're going to have to turn those evaporators off at some stage in order to run a defrost cycle. So how do we manage humidity in the space? Well, this is what we can achieve. And so this is the picture that we saw earlier where we got fogging appearing. And we take the air out of that store and we run it through a dehumidifier. And actually it doesn't take an awful lot of moisture removal to rapidly reduce that fogging. And this is running a dehumidifier for 20-25 minutes. And we can reduce fogging really dramatically. In the right-hand picture, we've got the photograph of our door with the accumulation of ice. But you'll notice that there's a duct on top of this. There we go, that's stainless steel duct. And what's happening is that that duct is attached to a dehumidifier. And dry air is then passed over that doorway. And what happens is the ice goes through the process of sublimation. Well, sublimation is when water goes from its solid form to its gaseous state without traveling through the liquid phase. So it's literally being absorbed by the dry air. It's not melting the ice, again, it's sublimation. It's taking the ice from its solid phase to its gaseous phase without passing through the liquid phase. So by passing that dry air over that doorway, we're absorbing that ice into the air. And again, we're freeing up those door switches and electrical components and goodness knows what else we are interfering with the ice. So if dehumidifiers are the solution, what kind of dehumidifiers do we use? Well, when most people think of a dehumidifier, they think of a condensing dehumidifier, which is a traditional direct expansion refrigeration cycle. And most of you will recognize the schematic here. You've got a compressor, that you've got a hot gas side, there's your condenser, a pressure change device, and you've got an evaporator where the liquid is going to evaporate. So you've got a cold coil here, and what happens, humid air comes along and hits this cold coil, and condensation occurs, and that condensation is dehumidifying. It's taking the moisture out of the air, and then that the refrigerant goes back to the compressor and the whole cycle starts again. So we've got warm, moist air going over an evaporator, drying it, and then the air goes over the condenser where it picks the air up, and that picks the heat up, and we get a slightly warmer air coming off it. So we get a slight heat gain from the latent heat of vaporization. But if we were to use this type of system in a cold store, we've got one mega problem, is that it would freeze in exactly the way that we see ice forming on an evaporator. So we can only really effectively use condensing dehumidifiers when our operating temperature is much higher and we're at a higher level of relative humidity. So we've got to think of another way. So with chill store and cold store dehumidification, we use a desiccant dehumidifier. So here we have our process air coming in from a cold store or a chill store. And that process air comes into a dehumidifier, and it hits a desiccant wheel. Now, this desiccant wheel is an incredibly high surface area that captures water molecules in the air, in their gaseous state. It holds onto those water molecules. So that air then has been dried as it passes over this desiccant wheel. The water molecules have been captured, and we get dry air going back into the cold store. Now you do get a slight heat gain as those moisture molecules release some of their heat as they're captured by that desiccant wheel. But it's not a huge deal. So we've got our dry air going back to the cold store. But that gives us a problem because we've now got a desiccant rotor that's holding on to all of this moisture. So how we get rid of that is that we take another line of air coming from outside, and we duct it through a fan and then through a heater. And we're going to heat that air up to maybe 120 degrees C. And we put that warm air over a section of that rotating rotor. And that air then dries that section of the rotor out. And we have wet regeneration air, which we then duct out to ambient. So we're capturing the moisture on this side of the desiccant wheel, but as it rotates into the much warmer airflow, that moisture is released. And a pretty good analogy is, when you go for a shower at home and you dry yourself off afterwards with a towel, you've taken the water off your body and you've captured it in a towel. Well, the towel here is our desiccant rotor. What do we do with our wet towel? Well, we put it on a wet radiator, and over time it dries out. And that's exactly what we're doing with our dehumidifier. We're capturing the water molecules and then passing them through a warm air stream to evaporate that water off and release it, and then we duct the moisture away. Now, cleverly, because we're capturing water in its gaseous phase, we don't need to worry about freezing. So we can operate between -40 and +40 degrees C, and between 0 and 100% RH. So it's a pretty good way of removing moisture from a chill store or a freezer store. And this is what the units look like to give you an idea of scale. And you can see the air coming back from a freezer store here. It's going to go through a desiccant wheel and then back to our freezer store, and just out of sight, you've got your regeneration air as well. Now, the great thing about this product is that we've got a PLC, a programmable logic controller with software that's going to control any defrost cycles that have to happen inside the unit. And we've got fans as well that we can control and optimize the speed of. So we can optimize the speed of both the fans, and we can optimize the level of heat, and we can optimize the rotation speed of the rotor. to give us the most efficient form of dehumidification that's optimized specifically for the cold store or the chill store in question. That means that an optimized system typically will use 55% less energy compared to just a standard unit that you're going to drop into your freezer store and dehumidify. So it's really critical to consider the sizing and the selection of the unit to make sure that we're matching those fan speeds, rotation speed, and regeneration heat as accurately as we can. So here you can see a picture of a dehumidifier, and this is mounted above the cold store. And you can see that we've got 100 mil thick insulation of the air that's coming from the cold store. So it's coming out of the cold store here, coming and running through the dehumidifier and then out again. And then this duct here is your regeneration air that's being taken from ambient. In this case, it's above the cold store. It's going through the dehumidifier and then out and being vented out to external. Now, inside this unit, we've got air that's coming from the cold store, so it's minus 27, minus 28 degrees C. So we have 100 mil thick insulation internally to stop any heat transfer. But even though you've got 100 mil insulation, if you've got a warm, humid environment on the outside of that dehumidifier, you have the risk of condensation forming on the outside of the unit. So it's good practice to mount it on a drip tray. And you can see that it's here below the unit. We've got the unit mounted on a drip tray that's just attached to a trap drain. So that just prevents any damage happening underneath the unit. Now, we mentioned regeneration heat. This is one of the critical aspects. There's two critical aspects of it. Obviously, the rotor and the technology within the rotor and the desiccant wheel is absolutely critical. But also the method of heat is critical as well. We use PTC heaters for the regeneration heat. And on a freezer application, it's incredibly important that they're waterproof. Some PTC heaters are not waterproof. All the ones that are on our units for these low temperature applications are waterproof, just in case there is any condensation in there. Well, the benefit of a PTC heater is that it's self-controlling. It can't overheat. So you don't have the requirement for really complex heat protection systems. But basically, as the temperature increases, the resistance in the heater climbs. When it reaches approximately 2 times our minimum, this generates the maximum temperature called the Curie point, or the Curie temperature, which is around 240 degrees C. We don't actually reach there, but because it's self-limiting, because the resistance climbs, its potential to generate heat reduces. So it's self-limiting. And it being waterproof, it's incredibly safe. So once we've got this dry air, there are various ways that we can deliver it and use it as well. In this example, you can see that we've got a duct that's attached to, that's being fed by a dehumidifier. And this duct, we've got a delivery slot for the air, and air is traveling over this doorway. And again, we're doing sublimation to get rid of any ice buildup. Ice was interfering with the mechanical aspects of the door, with the opening and closing mechanism, and interfering with switchgear. So by just putting that blanket of dry air over that doorway, we sublimate the ice away. Again, we're taking that air, that ice from its solid phase to its gaseous phase without going through the liquid phase. And this one was quite interesting. Actually, we've actually got 2 doors. It's got the main door to the cold store, but they'd also got a conveyor door where we got a constant feed of goods coming out when it was in production. And so we got a further airline, so it's coming down from the dehumidifier going right, and it's going left, and that left duct is going to this conveyor opening. And again, we're putting dehumidified air down over that opening to prevent ice build up on that strip curtain and preventing that strip curtain being ineffective in clinging together. Okay, so what are the options? Well, we then start to look at what kind of application you're looking at. Where are we going to put the dehumidifier? So on these slides, if I draw your eye to the right-hand side, and we've got a blue box here, and this blue box represents your freezer store. And here we've got a dehumidifier that's installed inside the freezer store. So air is going to be brought in over a filter, inside the dehumidifier, over a fan, and then pushed over the desiccant wheel. And that desiccant wheel is going to capture that moisture. So we then have dry air coming back and into the freezer. Nice and straightforward. Units coming in, over the rotor, and then out again. But we've got to deal with our regeneration air. So we're taking regeneration air from outside in through a filter, over a fan, then over our heater, then over our desiccant wheel, and then releasing that wet air, and that regeneration air being taken out to ambient. Now, this is kind of the traditional aspect of it, but there are some downsides. On the upside, we don't have such a temperature difference between the inside and the outside of the unit, so standard 30mm insulation is all that's needed on the internal side of the dehumidifier. But we can't have a programmable logic controller option here because the temperature is too cold for the PLC. So I can't optimize the system. I can't optimize the fan speeds, the rotor speeds, and the coil. So it becomes less effective, less efficient in its operation. Your regeneration duct does require 100mm insulation because you've got that warm, moist air that's still traveling out of the cold store. So we've got to make sure that we don't get heat transfer through either of those ducts. So we must have at least 100mm insulation. And it's got to operate continuously to make sure that it doesn't freeze up. And of course, it is in the freezer store, so it's difficult to service because it's -27, -28 degrees C. And really critically, it takes up valuable storage space within your freezer. And you're actually paying to keep that unit cold. You're cooling down that dehumidifier unit as well. But there are some other options. Again, if we look on the right-hand side here, and we imagine that this blue area is our freezer store, we could mount the dehumidifier outside of the freezer store. We could take our process air from the freezer store into our dehumidifier through a filter and a fan, and we capture the moisture, and then we send that dry air back into the freezer store. And our regeneration air is coming from ambient, going back into the dehumidifier over a filter and a fan, over the heater, and drying out the rotor, and then being sent outside. So, firstly, there are a couple of things we need to consider here. We have got air at -27, potentially, maybe even colder, going into this unit, and this unit is in ambient conditions. So we've got to have 100mm insulation. So make sure that we don't get ice forming on the inside of the dehumidifier. So we have that 100mm insulation. We also have a thermal bridge isolation. So any bit of metal or any item within that casework that could be a thermal bridge and have a good heat transfer, we isolate that and insulate it to prevent that thermal bridging happening. Again, as we saw in the photograph, you should put it on a drain tray to make sure that any possible condensation that forms on the outside of the unit doesn't drip down and damage anything that's underneath it. But critically here, the PLC option is available. So you can optimize the rotor speed, optimize the heater, optimize the fan speeds with EC fans. So that makes it a more efficient system. And of course, it's easier to service because it's not in the freezer store and it's not taking up valuable space in the freezer store. And of course, it can be shut down and just dampers closed. So that is another option for you. And here you can see a typical system. We've got our regeneration air here and our supply air here. And this unit is outside of the cold store, so you can see it's got the PLC control fitted to it. And it's quite a nice insulated set of ductwork. And here's another system here. You can see we've got the supply and return air, and we've got the dampers, so we can balance the airflows as well. There is another option though. You could, if you've got an adjacent chill store, mount the dehumidifier inside the chill store. Now this is quite a nice way of doing it, because we can put the dehumidifier in the chill store and actually dehumidify the air in the chill store. So here, if you can see, if you can imagine on this drawing, we've got the freezer store area, and then perhaps we've got a production area, or we've got a chilling area. So a freezer store maybe at -27, -28, and chill store, let's say 1-2 degrees C. Well, here we're taking process air in from the chill store over a filter and a fan. We're drying that air and then sending it back into the chill store. And we've still got to get rid of the moisture, so we have regeneration air coming in from external, going in over a filter and a fan, over our heater, and then hitting our desiccant, drying it out, and we're taking that regeneration air out. Now, the quite interesting thing about doing it this way is that if we dehumidify the air in the chill store, when they open the door to the freezer store, the air is much drier, so the potential for ice forming on the evaporator in the freezer store is vastly reduced because we've done the dehumidification in the chill store. So just by doing the chill store, you're reducing ice buildup in the evaporator in the chill store, but also concurrently reducing the ice buildup in the freezer area. And you can do this with the standard unit because there isn't that much difference between the internal and the external temperature. So standard 30mm insulation is absolutely fine. And you can use the PLC version because it's not too cold. So we can optimize those rotor speed and fan speeds and heater power draw. Well, it's easier to service, and again, it can be shut down. It doesn't have to be left running all the time. You can take air from the chill store and run it through a dehumidifier and feed that air into the freezer area. But beware, because we're going to have different dew points, and we could have condensation forming in our ductwork. So it is one to be a little bit cautious of. So again, supplied duct dew points must be below the store temperature, otherwise we run the risk of ice forming. But we do have the other benefits of having it in the chill store. So 30mm insulation, and you can have a PLC option, and it's easy to access. And again, you can turn the unit off. Blast freezers are more challenging. With a blast freezer, we've got low temperatures, -30 to -40, in very high air volumes, as we've got product either going through a spiral blast chiller or a conveyor blast chiller, and we're reducing the temperature of that product very, very quickly with high air volume. Now, when we get down to these lower temperature conditions, you've got to have specialized fans within the dehumidifier to make sure that the grease in the motors will not freeze up. And there's a very high condensation risk with a blast freezer. We've got an open-ended process here. So you've got moisture that's going to come in. And so our moisture leakage is going to be very high. So it's more difficult to maintain a low relative humidity or lower relative humidity in a blast freezer because we've got this much bigger difference in temperature, much more turbulence in the air, and those two constantly open in and out ducts. So you can do it by putting a dehumidified air and presenting that straight onto the evaporator. You do get some sublimation there with the ice, but it's much more challenging. So there's some of the ways that we do it. What about energy considerations? Well, okay, a small unit, DA500, 4.5 kilowatts. Actually, when it's optimized, it's probably looking at about 2.5 kilowatts. But it's important when you look at these kilowatts to know that if you want to defrost 1 kilogram of ice, that is going to cost you around 17 kilowatts of energy. So then we look at the amount of ice that we're preventing or we're sublimating or we're reducing. Actually, our power input to the unit, especially if you're using electric heaters as your defrost, then an optimized system can dramatically reduce the energy input. Typically, it's around a 25% decrease in energy, but there are ways to make it even more energy efficient. Here you can see a dehumidifier where we've got our supplier coming from the cold store, coming into the dehumidifier, going over the rotor and being dehumidified and dried and then going back to the cold store. But here you can see the regeneration air. And the regeneration air, before it gets into the dehumidifier, is hitting a condenser coil. And that is a bleed off the refrigeration system. So we've got hot gas putting waste heat from the refrigeration system into our regeneration air. So we're preheating that air before it gets to those heaters. So the heater doesn't have to draw as much power. So we're utilizing that waste heat that ordinarily our condensers trying to just reject, but we can utilize it here with the dehumidifier and make the whole system more efficient. And also you can see here, it's quite a nice installation. The dehumidifier is mounted above a cold store and it's mounted on a drip tray which is suspended on some drop rods. And then you can see you've got a little drain that's gone to a tank and that condensate is potentially pumped away. So a really nice installation, and again it's utilising that waste heat from our refrigeration system. But we can get even smarter. So if we imagine this is our dehumidifier and we've got our wet air coming from our space, going through the dehumidifier, moisture is captured by the rotor and then goes back into the freezer store. But our regeneration air is coming in, it's being heated up, we're drying out our rotor, and that air is then being sent out to waste. So what if we put a cross-flow heat exchanger here? And we warmed up one side of that cross-flow heat exchanger from that rejection air. And then we put our air inlet for the rejection air on the other side of it. Well, then we can scavenge that heat. We can recover that heat. So this heater doesn't need to work as hard. So suddenly that 25% saving can really dramatically reduce by firstly optimizing the system, and secondly, looking at utilizing either cross-flow heat exchanger, so we're rescuing some of that heat from regeneration, or we take a bleed off of our condenser coil, and we can utilize that waste heat as well. So finally, let's look at sizing and selection. What do we need to know in order to solve this problem? Well, firstly, we need to know how big the room is. What are the room dimensions that we're looking at? And we also need to know what are we doing to mitigate the ice that's the moisture ingress. Are we using air curtains? Are we using strip curtains? Are we using fast-acting doors? What are we doing to mitigate the air that's going to come through this door? How many doors are there? What is the actual operating area of the door? So just because the doorway is X by Y, actually the opening may be smaller than that. And the really critical one, how often are those doors open? This is the really tricky one. Have you got a really robust regime in your cold store that's going to make people close the door? Or are they propping the door open, worst case scenario? Have they got a good regime that if they're opening that door, they've used it, they're closing it as quickly as possible? And then we're going to need to know what is the temperature and humidity difference both inside and outside, ideally for winter and summer. And that is going to tell us the difference in vapor pressure between the two areas, and is that in conjunction with the size of the orifice is going to dictate how much air is going to be forced into that freezer or cold store. And we know that air has a certain moisture content, and so we know that moisture is going to be deposited as ice on the cold surfaces, be it the ceiling of the cold store or the evaporator coil or the product. So we're coming to the end of the webinar. The key takeaways for today is, firstly, you want to accurately assess the cost of high humidity, the cost of that ice forming in your system on your evaporator. Are you using electric heaters to defrost? Are you using hot gas? What is the cost of that? Are you, heavens forbid, do you have a fridge engineer that's getting up there with a turbo torch that's melting the ice? Have you got somebody in there, that cold store that you're sending in to scrape the ice off the ceiling or the floors? All of these things happen. So assessing what the cost, both in energy and of course in health and safety. Are we putting our staff at risk by allowing that ice to accumulate, or indeed that fog to accumulate? So then we decide on the product technology, and we've kind of done that with our looking at either condensing or desiccant. And we know at these low temperatures, it's a desiccant technology that we want to be using. Then we need to decide on the installation strategy. Are we putting it inside the cold store? Are we putting it outside the cold store? Are we putting it in a chill room and then feeding and dehumidifying the air in the chill room that's then preventing ice forming on the evaporators in the freezer store? And then we consider any energy saving options. Can we take a bleed off of our fridge system and put a condenser coil in the regeneration air? Can we use a crossflow heat exchanger? And then we gather the information for sizing. What are the size of the doors? How often are the doors open? What's the size of the store? And what's the temperature difference and relative humidity difference between inside and outside? So once we have that information, we can provide a selection for you for providing a dehumidifier to solve your icing up issues and make your freezer store a safer place to be. So thank you very much for bearing with me through the webinar. I know everybody's really short of time, and all your time is really precious, so I do thank you very, very much. Condair provides solutions for 3 technologies for both humidification, dehumidification, and evaporative cooling, and we've got several, if not many, hundreds of years of combined experience in dealing with these issues. So if you do have an application for humidification, dehumidification, or evaporative cooling, please drop us a line or give us a call or fill in the form on our website, www.condair.co.uk. So thank you very much, and now I'd like to open it up to see if we have any questions.
Hi, Dave. Thank you very much for your presentation. That was extremely useful, and we do indeed have a few questions. So if you wouldn't mind, start with a question from a gentleman called Alexander, asking, what is the standard expected relative humidity inside a cold room with a temperature of -18 to -24 degrees C?
Well, that's a really good question. Well, we have to remember, if we go back to our slide where air is contracting, that the air, when it comes in, is going to be much, much colder than it was when it's outside, and it's contracted due to that change in temperature. So when the air comes into that cold store, typically it's very quickly at 100% saturated. Now, when you close the door on the cold store, the refrigeration system is going to be working. We're going to be evaporating that refrigerant at those lower temperatures. We've got that cold surface, so moisture is going to form potentially on the ceiling or on cold surfaces. So we can expect the relative humidity to drop slightly as ice starts to form on that evaporator and starts to form elsewhere in the cold store. But it's not going to drop dramatically. It's still going to be very, very high.
Okay. No, that makes a lot of sense. Thank you. We do have a sort of double-decker question actually from a gentleman called Jeff. So the first part of the question is, if you are doing recirculation on a cold room with a dehumidifier, how do you overcome vapor pressure difference from infiltration from ambient? Would you partially give positive pressure?
Yeah, you would. You want to prevent ambient infiltration at all costs. Of course, it costs a lot of money for ambient infiltration. The bigger problem for us when in a dehumidifier, not a problem, but an issue we need to engineer around, is making sure that the regeneration air and the air that's being circulated through the rotor is balanced. We don't want a difference in pressure between the two air streams, because it's just a rubber blade that's separating those two airflows. So if we don't get the pressure right in the regeneration air and the air coming from the cold store returning to the cold store, then air could bleed through from one to the other. So that's more critical for you. But in answer to your question, yes, we want to maintain positive pressure.
Good, thank you. And the second part of that question, again from Jeff, is do you come across many cold stores with pressure relief valves fitted, given the reduction in vapor pressure? So basically to make sure that the differential in vapor pressure doesn't happen too much.
Yeah, I mean the vast majority of cold stores that I come along are generally standardly fitted with a pressure localization valve to make sure that even when we're closing and opening the doors, that any difference in pressure is accommodated. So yeah, and sucking air in through that vent again can be a source of ice formation because you're sucking warm, moist air through that vent.
Yeah, perfect. And one last question for you, actually, Dave, if that's okay. This one is from a gentleman called Stephen, and he when you are looking at a desiccant dryer fitted with a heat recovery option, does the regeneration fan have to be of a high temperature function? So in other words, does it have to be a specific fan up to potentially 50 or 70 degrees rating instead of the standard?
Yeah, it's not a specific fan, because even though we're doing heat recovery, we're not getting any hotter than we'd expect it to be. And the fan will be able to cope. Oh, I see what you mean, because we're putting that hot air onto the fan before the. I mean, I'm going to open that up to you, Julian. When you've done these selections, well, what are your thoughts on that?
I do think it all depends on the type of the type of heat recovery system that you're using and its efficiency, and how much heat do you actually want to put onto the fan. How much energy is there really that much of a benefit to heat the air up so much that through a heat recovery that I mean, in my opinion, the regeneration heater will still be doing most of the heating. And obviously, as the air goes through the desiccant rotor, it will have the adverse effect of desiccant drying, which is adiabatic cooling. So effectively, as much as your temperature on the outlet of the heater will be very high, on the outlet of the desiccant rotor, it will be significantly lower. So then by that point, and by the point as you then go through a heat recovery system, which will mix with outside air, which is probably likely to be cooler than your region air outlet, by the time it gets back to the region air intake, it's very unlikely to be that high. The temperature is very unlikely to be that high, particularly if the system is well balanced and you're already very aware of energy consumption. You wouldn't want a region air outlet that is too high. So it's a good way of backing up and of not using too much of the heating power from the PTC heater. At the same time, it's never going to reach such high temperatures. My guess is, yeah, you might want to go for a 60 degrees rated fan just in case, but if effectively, how likely are you to get to that maximum of 60 degrees rating is probably very few times.
Yeah, you're absolutely right, because as you quite rightly say, you've gone through an adiabatic cooling process on the regeneration air. So that air has probably hit the rotor at 120 degrees C, but it's probably coming off it at 50 degrees C. And then when it goes through the heat recovery system, and the heat recovery system is, let's say, 70% efficient, so you get 70% of that delta T. So you're probably coming back around onto it at maybe 40 degrees C, 45 degrees C. So it's not a dramatic effect on the fan. That's a long way around to ask the question, but it was a useful discussion.
Absolutely. Okay, we've actually got a few more questions. Do we have a little bit a bit more time?
We've got time for one more, Jules.
Yeah. Okay, so coming in from Darren this time. Is it a preferred option to install a dehum pulling air from airlock rather than pulling from the freezer room?
Yeah, if you want to put it, if you want to draw air from the airlock or the chill store before it gets to the freezer store, that's quite a nice way of doing it, because you can mount the unit inside the chill store and you get the added benefit of preventing ice forming up on the evaporator in the chill store, and you've removed that moisture before it has the opportunity to migrate into the freezer store. So yeah, it's a nice option to do if you can do it. You do have the option of still having an optimized system, because you can still have a PLC option and you haven't got as much insulation to have to consider. So yeah, it's a nice option if you've got the room and the space to do it. It's a nice option to do.
Good. And then one more, maybe, Dave, is that okay?
Squeeze one more in.
Squeeze one more in, okay. What about the temperature of dry air after the desiccant wheel? Does it affect the calculation of the freezer? I mean, does the freezer designer has to take into account the heat emission from the dry air, or is it minor? Thank you.
I mean, it is a really good question, because it isn't almost an adiabatic process. So as you're capturing those water molecules in the desiccant rotor, you are releasing heat energy. As that rotor captures the moisture molecule, it holds it still, and that heat energy, of course, is the vibration of the water molecule, and so heat will go into the freezer store. Typically, it's not a huge amount. I mean, we're talking maybe 750 watts, maybe 1.5 kilowatts, something along those lines. Nothing that the freezer store wouldn't be able to cope with. It is a consideration in the overall energy usage, but it's relatively minor.
Okay, perfect. There are a few more questions, but I do believe we are getting close to the end time. As you said, we're very aware that everyone is getting everyone's time is getting tight. So I would suggest we're taking notes of all the questions, and I would suggest that someone will then get back to everyone with the relevant comments a bit later on via email or via phone call, if that's okay.
Perfect. Well, again, thanks, Jules, and thank you again to everybody for joining us. If you do have an application, please contact us on condair.co.uk for humidification, dehumidification, or evaporative cooling. And again, thank you, Jules. Thank you to everybody. I hope everybody has a super day. Thanks again.
Thank you very much indeed. Bye, everyone.